All right, so the linear programming problem is you minimize some vector times your variable. So f is just a vector of weights. X is the variable we're going for. So it's, in the case of window design, it's our window samples. And then, so we're minimizing that. If we're minimizing some error in the frequency domain, then that vector might be just a vector of sampled cosines at some frequency, specifying the frequency response magnitude in the side lobe region, for example. And then we have all these constraints that we can specify. So you have equality constraints, which are in the form of AX plus B, AX equals B. A here is a matrix, B is a vector. And so these are equality constraints, and we also have inequality constraints. And those together give us the space of problems that we can solve. And let me just fast forward to an example so that we can see what these matrices look like filled in. Let's see, what's the simplest case? Maybe this one. All right, so here's what our window problem is going to look like. H is half of our window. It's the the unique sample. So we're working with symmetric windows. So we'll just design half of the window, and the other half we'll obtain by flipping the first half. And then delta is essentially the side lobe ripple. And so this is what it looks like. Minimize the ripple. So we just pluck out delta, the ripple, and say that's what we want to minimize, subject to these constraints. And so this first one is essentially keeping the frequency response between plus and minus delta. And I'm going to derive this in more detail. And then, so that's an equality constraint. And then here's an inequality constraint, which is essentially saying we want the window to be non-negative. So that's where we're saying minus h is less than or equal to 0. We're just getting it into the standard form. And then this matrix here multiplies h and delta and is non-negative, and that must be actually the frequency response magnitude being less than or equal to the ripple delta. So that means this one, oh yeah, this one up here is nothing more than scaling the window. You'll see, I'm going to show you that. Scales the window so that it has a unit DC gain. So now, if you want to solve one of these problems, well, what do you do? Well, in MATLAB, you can call linprog, and that will give you a solution to the linear programming problem. So all you have to do is come up with these matrices and vectors. So we come up with F, we come up with the matrix for our equality constraints and our inequality constraints. And you don't have to have them all. You can have any subset of these, and it will crank out the solution for you. All right, so here is just the help page for MATLAB's linprog. So you can say help linprog, and it will print all this stuff out. I'm not going to go through it, but you can see that it's the same basic formulation I just showed you, and it documents the various argument options and so on. So you can use that. There's the next page. Now, there's another option which is called CVX, which you can say is a contraction of convex. And this is an implementation of what's called discipline convex optimization. And so this toolbox was developed by Stephen Boyd and his groups in the EE department here. And we should have it on the Karma machine. So if you try to run it, it should be there. And so you assemble the matrices exactly the same way as for linprog, but then you have this this syntax in MATLAB, which is that the vector f is in transpose form, and then you create a begin-end block and declare your variable that you're optimizing x of n, and then you say minimize f times x subject to inequality constraint, equality constraint. So it's a very natural syntax. So it looks very much like what you would write down, or actually what you would say in describing the problem. And there's a whole range of advanced techniques there. There's a EE class on this. What is it, EE 363? Does anybody remember the number of the optimism? 364. Thank you. Yes, so EE 364, if you really want to get the the whole story here, and that is taught by Professor Boyd. And you can also buy his book, and you can download the software and so on. So if you really get into this stuff, these are some trailheads for you. All right, so now let's take our Chebyshev window problem and design it using linear programming instead of the closed form solution by Dolph.